I think that everyone is settled down, so we can start. Today, I'm going to present the talk about B-tree indexes, which are the heart of Postgres, in my opinion, and I'll try to share this idea with you. So first of all, the agenda of this talk. At first, I want to talk a little bit about Postgres indexes in general. So what are what's their difference between, what their difference from other maybe databases that you are familiar from. Then we'll talk a little bit about internals of B-tree indexes that will help us to understand optimizations better. And after this, I'll present two B-tree features, which are one of which is very brand new, and another is just a new feature. And yeah, we'll go into details of these two features. So a little bit about me. Let me introduce myself. My name is Anastasia. I work in Russian vendor company, Postgres Professional, as a Postgres contributor and core developer. So I work there since 2015, and I contribute to Postgres in different ways. I do write code. I develop some features. Those ones I will talk about today. And also I speak at conferences and teach databases at university. So today, currently, I focus mostly on indexing and storage optimizations, and also on backup solutions. So let me briefly remind you some important things about indexes in Postgres in general. So the first thing is that all indexes in Postgres currently are secondary indexes. It means that the index file is physically separated from the table that it describes. So typically, index stores a key that it indexes and also a pointer to its location in a heap, which is called tuple identifier or tuple ID. Index files are divided into standard size pages, and page layout is defined by access method. We have several access methods, such as B-tree, gin, gist index, also brin, and others. Today, I'll concentrate on B-tree. Data type support is provided by opclass. It's special object in Postgres database, which defines how exactly this data type will be compared with this access method. So obviously, you compare integers and text data in different way, and opclass is responsible for this implementation. Index in Postgres can be regular indexes. They also can be partial indexes that cover just a subset of tables data. They can be expressional indexes that are useful for queries that match some function or some modification of data. Here is some more information. Basically, we have some rules about indexes, and as you can see, every rule has an exception, has its own optimization. So by default, there is no visibility information in indexes. So regular index scan, to perform regular index scan, Postgres needs to access at first index and then recheck the visibility in heap table tuple. One optimization that allows to avoid heap access is called index-only scan, and it uses special structure visibility map to check that all information can be retrieved from index directly without accessing heap. This allows to save some disk access and speed up the query. Next point is about MVCC rules. According to MVCC rules, update overall always creates new version, all new index entry, except hot updates, which we will discuss later. Dead tuples that appear because of these MVCC updates are deleted by vacuum operation, and it also has an optimization that is called Microvacuum. It's a special flag. It uses special flag to mark dead tuples and to avoid recheck while vacuuming and to delete them faster from index. So let's move to B-tree. B-tree structure was invented in 80s. It's very mature data structure which is in use in many databases and other systems. B stands for balanced tree, and in Postgres we actually have B plus tree modification, which means that only leaf nodes contain keys and pointers to heap, while internal nodes only contain pointers to lower level of the B-tree itself. So all keys are sorted inside each node, and all leaf nodes are linked with each other. So this makes this data structure very efficient for point and range queries. In Postgres, B-tree is used not only to satisfy queries that compare values, like for equality or larger or smaller values, but also to speed up order by clause and table joins. Also, B-tree is default index type, and currently it's the only index type that can be used for unique and primary key constraints. So this is the core functionality of database engine, which makes B-tree a very important component. As a default index type, B-tree is used to support system indexes and toast indexes. So even in empty database, like in absolutely new empty database, you already have more than 100 of B-tree indexes, which support Postgres catalog. B-tree implementation in Postgres is based on this paper by Lehman Yao. This is like the very old one, and it has some assumptions. Some of them are met in Postgres, and some are not. So the idea of this paper, the modification to regular B-tree, is that every leaf page has right link pointer to its right sibling, so that we can read through leaf page level. Also, it introduces the concept of a high key. This is an upper bound of the keys that are allowed on this page, and this also allows to answer those queries faster. So you can check whether there are more data on the next pages or not. And also, it has an assumption that we can fit at least 3 items per page, which is met in Postgres. It's just to keep the B-tree structure like tree, not a list. And also there are some more assumptions that are mostly theoretical. They do not match reality, like Postgres reality. This Lehman Yao paper assumes that all keys are fixed size. It makes most of the theory simpler, but in Postgres it works in a different way. Also, it assumes that in-memory copies of 3 pages are unshared, so it doesn't bother with locking and all that stuff. And finally, it assumes that all B-tree keys are unique. So mostly B-trees are used to support constraints, to support unique or primary key constraints. So this is fine for theory, but not exactly true in practice. So major ideas of Lehman Yao algorithm are implemented unchanged to have both right links and high keys. But in addition to the right link, we also store a left link pointer that is used to do backward index scans. So for example, when you do order by in descending order, you can also use the same index, just follow another direction. Also, keys in B-trees, in Postgres B-trees, are not fixed size, so maximum number of keys is defined with some special macro, and this is actually a restriction of Postgres B-tree, which means that you cannot fit into your B-tree any data, any row that is larger than 1/3 of a page. So it's approximately 2,000 bytes or something. Yeah, it's approximately 2 kilobytes. So if you want to index some larger values, you will probably need to use some expression or functional index. And the last point here is that all pages in B-tree are shared. They are located in shared buffers, so page level read lock-in is still required. We also need write lock-in when we update the pages. So sometimes it's also a performance issue when too many writes into B-tree create some contention lock. If you want to dig into more details, you can check B-tree README, which contains all information about the similarities to theory, the differences, and very much information about the exact implementation of Postgres B-tree. Next specific detail is about assumption of unique keys. So even unique B-tree index in Postgres actually can have non-unique values because of MVCC copies. To differentiate, to disambiguate multiple occurrences of the same key at the same level, we use the link, this tuple ID field. So yeah, this tuple ID is used as unique identifier. In Postgres 12, this stuff was heavily optimized. It's mostly internal optimizations, so they are not exposed to user level. You cannot set up them or something. They're just there. And if you want to learn, they're unfortunately out of scope for this talk. If you want to learn more about them, you can check this article or Postgres documentation. The idea of this optimization is that now tuple ID is considered just to be one more column of this index. It's just simplifies the implementation of B-tree algorithm, which is always good to simplify things because you can, you will get less errors while coding, and also it improves performance when you work with some specific workload. For example, when you insert many subsequent values into your B-tree index, which is usually something that you do with primary key ID. These new indexes will be smaller, and this split after new tuple optimization is responsible for this. So thanks for Peter Gigan, who implemented this stuff in Postgres 12. Some more Postgres B-tree features that I simply have to mention somewhere. Since version 11, Postgres provides an ability to create indexes in parallel, which dramatically improves the usability on large database deployments. So you can use multiple CPUs to create your index faster. This currently only available for B-tree. And also one more feature of B-trees is ImCheck extension for index verification. So if you attended Robert's talk about possible database corruption, you know that it's always good to have some, one more tool to check that everything goes well in your database. And you can use this ImCheck tool with your Postgres indexes to ensure that their logical and physical structure is correct, that it's not corrupted. This ImCheck tool also supports any optimizations of indexes, so you can use it with any other index. So, let's move to the features, to the major part of this talk. First of all, I want to describe covering indexes and how are they implemented in Postgres. Actually, covering index is not the feature itself. It's rather an idea based on combination of two features. So we have multi-column indexes and we have index-only scan. And if we combine them, we can get covering index. Multi-column B-tree index present in Postgres since the beginning of time. They were there always. And they allow multiple keys to be stored in a single tuple, and so that they can satisfy queries that access both fields. So for example, if you want to select something with clause on A and B on both fields, you can use this query. Index-only scan is the optimization that allows to retrieve data not only from directly from index without any extra access to a heap. If you have large index, if you have large table, and not everything in your database fits into memory, this can save a lot of I/O operations and speed up queries and improve performance. So here is an example of covering index. Let's say you want to retrieve both fields A and B from this table, and you only have this where clause on A field. You can create index on both fields. It will be multi-column index, and this setup will use index-only scan optimization. What's the problem with covering indexes? So first, the major problem is that usually you already have some unique index on your table. Like most of the tables have primary key or something, or some unique fields at least, and you have to have this unique index. It's created implicitly. It's also B-tree. So even if you haven't created this manually, it's already there. You have this unique index on, let's say, 2 columns. And let's say you want to use this covering index optimization to speed up your queries that access C3 column. So you created new index, new covering index. The problem with this setup is that we have a lot of duplicated data. We have to maintain 2 indexes instead of 1 index. It's just doubles the space taken by indexes. It doubles the space in memory that those indexes will use. And also, this slows down the insertions and updates, because every insertion into your table it also means insertion to your index or to multiple indexes if you have them. So here comes the new feature. It's called index with included columns with keyword include. And it allows you to combine those 2 indexes into one, to merge them into one physical index. So you can create unique index on these 2 columns, and also include some payload column with include keyword. So this is basically the same as on the previous slide, with the difference that you don't have to maintain 2 indexes. You now have much less space taken, and you still can perform these queries as fast as in previous example. So keyword include specifies a portion of columns on which the uniqueness is not enforced. So included columns, they exist only to allow more queries to benefit from index-only scan. You can also create non-unique index with such included columns, but to be honest, I don't see very much use of this kind of feature. It's also possible to create constraint with included column index. You can see it at the bottom of the slide. So you don't have to create index and then alter table to use this index. You can simply write it in table definition, table detail definition, so it will use this index with included columns. Also, you can use the same syntax with primary key constraint. So what are the benefits of this feature? It allows to combine constraint and covering index and decrease maintenance overhead. Since size of the index becomes smaller, inserts are faster, and everything is just good. Also, one more benefit is that it allows to add into index some data without B-tree op class. Let's say you want to query some some information, some, let's say, geospatial information from your table by ID. Or you may want to query some specific data type information from your table by user ID. And you want to use it with index-only scan because it's like the query that you do really often, but you cannot build index on this specific data type. You can store this data type as a payload in index with included columns. Index ordering won't apply to these included columns, so when you really need multi-column index that will support ordering on both columns, you should use multi-column index. But if you want just to add some payload into this index, you can use index with included columns. To understand the drawbacks of this feature of these covering indexes, we need to learn about one more optimization of B-tree indexes. It's heap-only tuple feature. So the idea of this feature is that it eliminates redundant index entries. So let's look at the example. Imagine that we want to update a row in index table, and it means that we also must insert some new entry into the index. So I hope you can see the bottom of the slide. In this, so let's say we have this table and this index, and we want to update indexed field ID, where we want to update ID 16, update ID 15, changes to 16. So, I'm sorry. Okay, so yeah, I think I need to explain the picture. So green is the index and yellow is the table, and reds are high keys in index pages. So those, can I use it? No. So those pieces are pages. They represent pages, like index pages, and each index page, except the rightmost, they have high key that restricts the upper bound of this page. So it means that there can be none keys that are larger than high key on this page. This allows to optimize some read queries to this index, and also supports concurrent insertions and concurrent page splits. So let's say we want to update field ID. When we updated the key, a new tuple was inserted into both table and index. So this is pretty much obvious. We cannot optimize it anymore. But if we do not change value of indexed column, new index entry will be redundant. So let's say we want to update data field for now, data attribute. If we have hot tuple optimization, we can simply add it into table data page and avoid adding new tuple to index. So this helps us to keep index smaller, and also like to avoid extra insert operations. There is so-called hot chain, which supports the links of those fields. So we have them linked in one heap page, and we can access them by ID. So when we perform search by key, we will at first access index. We'll find that we have ID 16, and then we access table and search for hot chain to find all the values. Can you use the mic, please?
So vacuum here will have one additional step. When we are doing a vacuum, that hot chain, to remove that hot chain?
No, vacuum does not. Vacuum will remove hot chain when it will be not visible for all tuples, but if it's still visible to some transactions, like some transactions can still see this tuple 16e, and some transactions are we'll see updated tuple 16k, and when it's not more visible to any transaction, it will be deleted by vacuum. So it's also somewhat optimization because the vacuum should not update index with those hot chains. It just updates table.
All right.
So now, as we see hot optimizations, it's very useful for heavily updated tables. We can conclude that indexes with included columns are good with read load. So I can say that it's a very good feature for read workload when you can enable index-only scan for read queries, but you should think twice before using it on heavily updated tables. Because if you have multi-column index or index with included columns, they are indexed, and you have to, you cannot use hot updates anymore. And here is like the trade-off. You can choose whether you want your select queries faster or you want your index smaller and your write queries faster. It's always up to DBA to decide. So if you have any questions on this part, I think I can answer them and then move to the next feature.
Please raise your hand.
So hard changes, where it will save in the page, because there is a change, hard change is been marking red color. For example, 16 to 16 hard chain. For example, again it moved to 16 to 16 instead of KF skin. So 3 hard chains was made. So where this hard chain details has been saved in the page.
So hot chain it's the detail of the physical implementation of the Postgres heap pages. So just every next tuple has some flag that shows that it has subsequent tuple, and it points to the next tuple in this chain, and thus we can find all of them. If chain takes more than one page, we have to split it and we have to add new value into index. So if you have like really a lot of updates on your field, so if you have more than 3 updates for this data field, we will have to insert new entry into index to point the next page. But in one page, we can form hot chain to connect those tuples. Okay, so let's go to the next feature, which is B-tree deduplication. And I'm excited to announce that it was committed just today, tonight. So it's officially the first talk about this upcoming Postgres feature. And are there any core developers in the room? I want to ask you. Yeah, so you'll understand me. It took about 4 years and more than like 50 revisions before this patch was actually accepted to Postgres core. As I already said, B-tree is is a very important component of Postgres, and that's cool because when you improve it, you can improve the experience of many people at once, but you can as well break everything for them very easily, unless this feature very well tested and reviewed. So any change to thus core components require a lot of testing and review, and I also encourage you to participate beta testing of upcoming Postgres version, so we were sure that this stuff really works well. So the idea behind this feature is very simple, actually. It's already, if you are familiar with gene indexes, it's something like posting list in gene index. The problem is that when we have index with a lot of duplicates, we have to store repeated key many times. And it takes space, and it leads to some degradation of index structure. So in this example, let's say we have very many duplicates of key 5, and we have to repeatedly store it, and it takes several pages in this, even in this example. If we apply this post-in list deduplication, we can just store key once, and along with it, we can store all the pointers to heap, all the tuple identifiers. So that's it. So the idea of the tuple is super simple, and I think that everyone understands how it should work. How is it visible to user? So it introduces new B-tree parameter, deduplicate 8 items, which can be set for every particular index. By default, it's enabled for all user indexes. It's disabled for system indexes for now, and we want to decide during beta testing whether we need some more option, let's say cluster-wide option to enable or disable the duplication. But as we decided in previous discussion, we can go for this default for now because the overhead is quite small. There are a few restrictions. So this deduplication relies on the binary equality of keys, and thus it does not support numeric, float, and container types such as array or record types. I think it's not a big deal because I don't think that really many people use B-tree indexes on record types or on something like this. We will try to work more on arrays because it seems to be important feature, but it does not support numeric and float because of the data type nature, because the binary equality of two numeric attributes does not mean that they are equal, that they can be showed equal to user. So this optimization, I think that's the major restriction because there are some B-tree indexes on numeric fields. So the duplication overhead is amortized across insertions, so it adds very few overhead, so it's only 2% on append-only benchmark, which can be considered the worst case. Again, I encourage you to test it with some more real data, and if you will help us to find some some worst cases, which we'll be able to improve. The duplication only applied when page is about to split. So we do not deduplicate tuples on each insertion. We only compress the page once per split. So some numbers from benchmarking. The deduplication from our benchmarks helps to transparently make indexes 2 to 4 times smaller. I think that's really impressive because you'll get this, it doesn't decrease other performance. It will probably help some indexes to fit into memory so that they will work much faster. And for TPCH benchmark, we can see that it saves 40% of space. We moved from almost 6 gigabytes of indexes to 3.5 gigabytes. And also, I didn't see any significant slowdown on index creation. So there is obviously some overhead because we have to compare values to understand whether they are duplicates or not. But this overhead seem to be eliminated because now we have smaller indexes and it doesn't slow down creation or insertion. So here is the actual numbers from TPCH benchmark. So you can see that those two indexes, which are not bold, they are numeric indexes, thus they do not use this optimization, and their size is the same, while almost all other indexes are 2-3 times smaller. Again, it's totally transparent to user. It doesn't change anything in logical structure, and still uses all the same optimization. One more thing I need to say is that this feature is not compatible with previous feature, which is index with included columns, and I think it's more or less adequate solution because usually indexes with included columns are unique, and thus they won't have that many duplicates. One more thing to learn about this feature is actually that it helps to support unique indexes. So we shouldn't have many duplicates in unique index, right? But still they can appear because of MVCC, because of MVCC copies. So let's say you updated your primary key and now you have 2 entries in your index. There is special optimization which is called Microvacuum or on-the-fly deletion, and it's useful to avoid page splits and index bloating when it's possible to speed up vacuuming. It works like this. So when we read index keys and recheck their visibility in the table, we can find that this particular tuple is invisible to all transactions. And we can mark them as dead tuples in index using special flag. After that, when we want to insert some new entries, some new key on this full page, before we do page split, we can check whether it has any garbage. And we can remove those tuples. We shouldn't wait for real vacuum operation. We can remove them while inserting entry. Thus, we can avoid split, unnecessary split, and make room for new entry and avoid index bloat. So this is where B-tree deduplication helps in synergy with Microvacuum. It helps to avoid index bloat because it gives some more time to Microvacuum to come and to notice that those entries are dead and that we can remove them and insert new entries. So basically, it just packs tuples on the page more densely and creates more space and more time for Microvacuum. So here is some numbers from benchmark with PGBench. So the idea was that we created a table and then created a table with an index and then run a lot of update queries on this index. And old index grew from 10 gigabytes, it grew almost twice, so to almost 20 gigabytes. While new index, in several hours of benchmarking, it grew only, let's say, 30%, which I think very good number. It means that in a long run, this feature helps to avoid index bloat. Of course, if you have very, very heavy updates on your primary key and Microvacuum does not cannot cope with it, cannot work on this space, your index will still load and grow. But for most workloads, this will help to keep index on some moderate size, and yeah, I think it's also very good thing, which was not expected when we started working on this feature, and just appeared in discussion, in review. So thanks to Peter Gigan for this particular feature. What's next? There are some even more features to expect for Postgres B-trees. First of them is Kainan search for B-trees. So for queries, when you want to find several points nearest to the point you query, you can use this optimization, and it will speed up such queries twice. in time. This patch is almost ready. It was blocked by this deduplication patch, and I hope we will see it in Postgres 13 as well. Index skip scan will optimize indexes in such a way that you'll be able to run distinct or order by queries much faster. So you won't have to recheck every duplicate entry, and you can just move from one distinct entry to another. I don't actually know what's the current state of this patch, but I believe that it will be in Postgres 14 for sure, but I don't know about Postgres 13. There are also some more index deletion optimizations. Let's say when you delete just a couple of entries and you want to vacuum index, you don't have to run through all data in index. You can just access specific entries. And the more global plans are index organized tables, like primary indexes and indexes on partitioned tables, which we are locked for now. Let's say global indexes on partitioned tables, or global partitioned indexes, which can be partitioned on some different attribute. Those are just future plans for B-tree optimizations. So that's all for now. Thank you. And if you have any questions, I'm ready to answer. Yeah.
Is Microvacuum completely a new feature in PG13, or is something there in PG12 also?
Microvacuum is pretty old feature. It was for sure in Postgres 11, and I think it's even older. So yeah, it's not new feature.
Any more questions?
Okay. So, thank you.
Thank you, Anastasia.